Hello, welcome to a video about reflection and refraction. Refraction is the change in direction of propagation of a wave as its speed changes. In stage 1 physics, you need to be able to describe reflection and refraction using the ray model of light. You'll need to be able to explain a range of light-related phenomena, including reflection, refraction, total internal reflection, and you'll need to be able to do this using the wave model. You'll also need to undertake experiments to investigate reflection or refraction of light using different media. So reflection is the change in direction of light at a surface. You can have specular reflection, which is where the incident light is reflected in a single direction, and this happens with smooth surfaces. So this example here is specular reflection. So all of the light rays are reflected in the same direction. You can get diffuse reflection as well, and this is where incident light is reflected in multiple different directions, and this happens with rough surfaces. The second example here is an example of diffuse reflection. The law of reflection states that the angle of incidence, which is the angle between the incident ray and the normal, which is perpendicular to the surface. So the angle of incidence is equal to the angle between the normal and the reflected ray, so the angle of reflection, which is here. So the angle of incidence is always the same as the angle of reflection. The reason that light is reflected in a single direction in specular reflection is because the normals are all parallel, regardless of where the light ray hits the surface, because the surface is smooth. So all of these light rays come in, and the angle of incidence between any one of these light rays and the corresponding normal is going to be equal to the angle of reflection, and all of these incident rays coming in are going to be parallel, therefore all of the reflected rays are also going to be parallel. On the other hand, with diffuse reflection, because the surface is rough, the normal, which is the dotted red lines, is going to be at a different angle depending on the exact point that the light ray is hitting on the surface. So the angle of incidence and the angle of reflection, they're always the same, but if the normal is different at a different point on the surface, then those angles are going to be different. So the angle of incidence, which is already outlined, I'm just going to go over it in blue, for the middle light ray, and that corresponds with the angle of reflection, which is the same as the angle of incidence. For the lowest light ray, the angle of incidence is here, and the angle of reflection is here. So the normal is obviously, it's still at 90 degrees to the surface, but because the angle of the surface is different, then the normal is at that particular angle. For the top ray, the angle of incidence is quite large. It goes from all the way from the top ray to here, to the normal, and then the angle of reflection goes from the normal all the way down to the corresponding reflected ray. So the angle of incidence always matches the angle of reflection, but if the surface is rough, the normal for each point along the surface is going to be different. Refraction is the change in direction of light due to the change in speed through different media. So the speed of light is dependent on a medium's refractive index, which is denoted as n, or represented with an n. If a medium has a higher n, then so a higher refractive index, then the speed of light is going to be slower in this medium. And this is because wavelength of light decreases as the refractive index increases. Therefore, the velocity of light will decrease. So if the frequency is staying the same, and that's because speed is equal to frequency by velocity. Therefore, if the wavelength is decreasing and the frequency is staying the same, then the velocity is also going to decrease. The refractive index is given by the rule n equals c divided by v, so it's a ratio of the speed of light in a vacuum to the speed of light in whatever the medium is. So the minimum refractive index is 1, so that's the speed of light divided by the speed of light, so c on c. Everything else that's not a vacuum will have a refractive index of greater than 1 because you can't go higher than the speed of light. Refraction is the phenomenon responsible for like water warping things. So when you look at like your legs in the bath or your legs in a pool or a pencil in a glass, the light refracts because the refractive index of water is different to the refractive index of air. So when you're looking at things in water, they appear different or misaligned. So the law of refraction states that the angle of refraction is dependent on the angle of incidence as well as the refractive index of the media. Something I just want to say and flag is that the angle of refraction, unfortunately, uses a theta and then a little r as its symbol, which is also what the angle of reflection uses. So if you want to, you're welcome to write like the first 4 letters of each word so you don't forget which angle you're working with. Usually you can tell from the context of the question, but I don't mind either way, but if it's easier for you to work with and remember, then you're welcome to do that for yourself. But something I just wanted to point out just in case there is any confusion. If light is moving from a medium with a lower refractive index to a medium with a higher refractive index, the light will move towards the normal, and that's because the light speed slows down. So for example, if we're going from air to water, the light will come in and you'll have an incidence angle here, and that light will move towards the normal because it's slowed down, and this will be your, I'm not going to be able to fit this in here, this will be your angle of refraction. So the light has been towards the normal because it slowed down from a lower refractive index to a higher refractive index. Conversely, if you're going from a medium with a higher refractive index to a lower refractive index, light will bend away from the normal because it's sped up. So if you're going from water to air, if you've got your angle of incidence here and your incident ray, then the light will bend away from the normal, and this will be your angle of refraction here. Snell's law describes the relationship between the incident angle and the refracted angle, or the angle of refraction and the angle of incidence, for light travelling between different media. And that rule is the refractive index of the first medium times by sine of the angle of incidence, and that is equal to the refractive index of the second medium multiplied by sine of the refracted angle. And you can use this rule for determining unknown values. So if you're trying to work out the refractive index of a material if you're trying to work out the angle of incidence or the refracted angle given any of the other values, then you'll be able to apply this rule. So for example, the speed of light in water is 2.25 by 10 to the 8 meters per second, given that the speed of light in a vacuum, so C, is equal to 3.0 by 10 to the 8 meters per second. What is the refractive index of water? So using our rule, we know that N, the refractive index, is equal to the ratio of the speed of light to the speed of light in the material, so C divided by V. We know that the speed of light in water is given to us, it's 2.25 by 10 to the 8 meters per second, and we know that the speed of light is 3.0 by 10 to the 8 meters per second. So to apply our rule, all we have to do is say N is equal to 3.0 by 10 to the 8 divided by 2.25 by 10 to the 8, and if you pop that into your calculator, you'll end up with a refractive index of 1.33, and that's the refractive index of water. Another example, a light ray strikes pool water with a refractive index of 1.33 at an incident angle of 30 degrees to the normal. What is the angle of refraction? So for this one we use Snell's law, so that's N1 sine of the incident angle is equal to N2 sine of the refracted angle. We know that N2, which is the pool water, is equal to 1.33. N1 is the air, so that's just 1. If it's not stated in the question, then you can presume that it's 1. The angle of incidence is 30 degrees, and we are looking for the angle of refraction. The reason that we know that this N here is N2 is because the light ray strikes the pool water and it's about to go into the pool water. So that must be the second refractive index. The first refractive index is air because the light is coming from the air and then going into the water. So we want to rearrange this rule to make our angle of refraction the subject. So rearranging this for the angle of refraction will be inverse sine of N1 sine angle of incidence divided by N2. This will be inverse sine of 1 multiplied by sine 30 divided by 1.33, and if you pop all of that into your calculator, you'll end up with a refracted angle of 22.1 degrees. So that's your angle of refraction in the water. So now we'll have a look at the critical angle. Just a reminder that light passing from a higher to a lower refractive index is refracted away from the normal. So we've got a light ray travelling from water into air, and the refractive index of water is bigger than the refractive index of air, so it's going from a higher refractive index into a lower refractive index. So the light will be refracted away from the normal. So the angle of refraction is going to be bigger than the angle of incidence. As the angle of incidence increases, the angle of refraction increases, and eventually you get to a situation where the angle of refraction is equal to 90 degrees, and this is called the critical angle, and essentially light is refracted along the interface between both media. So just to reiterate, when the angle of refraction is 90 degrees, the angle of incidence is called the critical angle. So this angle here. You can use Snell's law to solve problems involving the critical angle. So for example, what is the critical angle for light passing from glass, which has a refractive index of n equals 1.5, to air, which has a refractive index of 1.0? So first of all, we'll start off with Snell's law, which states that n1 multiplied by sine of the incident angle is going to be equal to n2, the refractive index of the second medium, multiplied by sine of the angle of refraction. What do we already know from this situation? So we're looking for the critical angle. So we know that the angle of incidence is going to be equal to the critical angle, and we're looking for this. If we're looking for the critical angle, then our angle of refraction must be 90 degrees. So that's like some hidden information in this question that you need to use your conceptual knowledge for. If we're talking about, I'm going to redo that degree sign because it's a bit mediocre, 90 degrees. Now the 0 is mediocre, but whatever. So if we're talking about the critical angle, then the angle of refraction is going to be 90 degrees. N2, so the refractive index of the second medium, is going to be air, because the light is passing from the glass to the air. So the first one must be glass, the second one must be air, so N1 must be equal to 1.5. Because we're looking for the critical angle, we're looking for this here, the incidence angle. So we can rewrite this whole thing. We can say that N1 sine of the critical angle is equal to N2 sine of the refracted angle. If you want to, you could sub in all of your values here and then rearrange the equation to find the critical angle. I prefer to rearrange first and sub in later, so I'm going to do that. So I'll get the critical angle is equal to inverse sine of N2 sine angle of refraction divided by, oops, that should be N1. Pop all of our values in. Inverse sine of 1.0 multiplied by sine 90 divided by 1.5. Sine 90 is equal to 1, so this will be critical angle is equal to inverse sine of 1.0 divided by 1.5, and if you pop that into your calculator, you'll end up with a critical angle of 42 degrees. So the critical angle for light passing from glass into air is 42 degrees. The last thing we'll look at today is total internal reflection, and this continues on from the critical angle. So if the angle of incidence is greater than the critical angle, so with the critical angle, light is being refracted at 90 degrees, so along the surface between the interface of the two materials. If the incident angle is greater than the critical angle, then no refraction occurs and light is totally internally reflected. So light is simply reflected back at the interface between the two media and back into the medium with the higher refractive index. This has application in fibre optics, and fibre optics allow for the transmission of visible light inside fibres, which could be made from plastic or glass. In fibre optics, light is refracted towards the normal upon travelling from air into glass. So the light travels slower in the glass of the fibre optic, so it is refracted towards the normal, and that normal is perpendicular to the entry point of the glass. The refracted ray is then totally internally reflected if the angle of incidence, which is this angle here, at the internal edge of the fibre is, and this should say, greater than the critical angle. So the angle of incidence needs to be greater than the critical angle so that all of the light is totally internally reflected. Light will then propagate along the tube via this total internal reflection, as you can see here. This is used in telecommunications. It's what the NBN uses. It's used in electronics. It's also used in surgical tools. For example, in keyhole surgery and endoscopy.